Thor, no one's learning about fluid dynamics under my watch.
Loki, it's time to bring down the hammer. Water hammer!
So what is water hammer effect? To begin, we have a pipe that contains a fluid that is currently flowing. We also have a valve that is opened. A flowing fluid has a specific amount of energy of flow. This is called kinetic energy. Now, if we were to close the valve, this will stop the flow abruptly. The water column that is close to the valve is not moving anymore, but the columns before it are still in motion. This creates a pressure buildup. This energy has to be dissipated somewhere. So a reaction wave, opposite to the direction of flow, is formed. This is the shock wave, which causes a boom. This is called the water hammer effect.
Isaac Newton postulated that force equals mass times acceleration. Therefore, when closing a valve on a pipe, force equals the mass of water times the change in velocity over the valve closure time. But when the valve is closed too quickly, this can lead to massive forces on the pipe. We all know that the momentum as water is given by the density times the flow rate times the change in velocity, but when the velocity out equals 0, that leads to a negative force as the water bounces off the end of the pipe and is forced in the other direction. The pressure at any point in the pipe at any point in time can be given by a celerity wave, which has a period of 4 times the length of the pipe over the speed of sound in the pipe. This is not to be confused with other types of celery waves. The speed of the celerity wave depends on the speed that sound travels through the system, and the pressure in the pipe depends upon whether or not the valve is closed before the wave returns.
Let's look at this in real life. We have a pipe here. This is the valve. We're going to shoot the water through here. We're going to close the valve quickly, and hopefully we'll see hammer effect develop in this tee. Okay? We're going to put the water in.
Ready?
And we close the valve.
3, 2, 1.
This video is brought to you by Oasis Cranberry Juice. Be pure. So I'm going to hit the top of this bottle, and the juice is going to move up and compress the air at the top while leaving a vacuum of air at the bottom. And like in the water hammer effect, the juice will bounce off the end of the bottle or the end of the pipe and shoot back down to the other side, and we'll see what happens. Yay!
Now let's talk about the effects and mitigation. The water hammer effect is similar in both residential and commercial applications. In residential applications, you'll mostly just hear a thud if the valve is shut off too quickly. If the water hammer effect is strong enough, the pipes can actually be blown apart. An example of this took place right here at the Fluid Dynamics Laboratory. While the pump was running, the valve was quickly shut and resulted in a glued-on elbow joint being blown off the pipe. The water hammer effect is also present in more extreme situations. For example, watch what happens when a storm drainage system experiences the water hammer effect. So how can the water hammer effect be mitigated or prevented? Apart from increasing the time to close the valve, water hammer dampeners are mechanisms to dissipate the energy wave generated. Residential water hammer dampeners are known as water arresters. They are installed just upstream of the valve in question. Surge tanks operate on the same principle and are used in commercial applications. Surge tanks generally consist of a water-impermeable membrane inside a pressurized vessel. When the valve is shut off, the membrane will expand and fill with water. The vessel acts to reduce the amplitude of the energy waves. Notice that the expansion of the membrane is reduced with each cycle. Now here's a quick demo. Watch for the balloon filling with water when the valve is shut off. On 3. 1, 2, 3.
Thank you for watching. Hope you learned something.
Now let's all go get hammered.
Oh, you mean water hammered?
Sure.